Hey everyone, welcome back to the final week of this Summer Physics 1 course. So today we're going to be talking about rotational kinematics, or basically how we describe the motion of things that are rotating. So rotational kinematics is important because, unlike what the first 3 weeks of this course might have suggested, right, things in this real world do not simply move about solely by sliding frictionlessly in 3 dimensions, right? So things in the real world, usually at one point or another, rotate in some way. Otherwise, how would your car function? For example. So as a matter of fact, most energy production in today's society involves some form of conversion between things moving linearly and things rotating. So for example, your car's engine has pistons in it that move linearly up and down or side to side or whatever, but they end up making the crankshaft of your car rotate, which in turn ends up allowing your car to move forward. For a hydroelectric dam, right, we take water that is moving forward, roughly in a straight line, and right, it spins a turbine, which is just a fancy name for a big fan. And by turning that big fan, we end up generating electricity. So rotations are pretty important. Bottom line is we need rotations and we need a way to describe them. So the great news is that rotational kinematics looks suspiciously like the 1D kinematics motion stuff we've seen from this course's second lecture, right? For every concept and definition in one-dimensional kinematic motion, you can bet that there's an associated rotational kinematic analog. So for example, I've got this little table here. And on the left-hand side, I'm going to be describing one-dimensional motion stuff that we saw in our second lecture. And on the right, I'm going to write down the rotational analog stuff. So in 1D, right, we dealt with things along the x-axis, for example. And here for rotation motion, the analog of our, defining our position on the x-axis is defining our axis of rotation. Right, so what are we rotating around? Rotation. Our displacement in the x direction, right? The rotational analog of that is our angular displacement. So instead of saying how far we've gone in the x direction, like our displacement in the x direction, now we're saying how far we've gone around our axis of rotation. Right? We also said that the velocity of an object is just the displacement in the x direction divided by the elapsed time, delta t. And the angular, right, the angular velocity, which is written as here, it's an omega, not a w, an omega. Right, this is going to be our angular displacement divided by delta t. So just real quick, this is the Greek letter omega, right, lowercase. And if you think, well, there's something for acceleration, you'd be right. So acceleration is defined as, right, the change in our velocity divided by the elapsed time. And there's also an angular acceleration, which says that the angular acceleration alpha is equal to the change in our angular velocity, so delta omega, there we go, divided by the elapsed time, right? So if something's angularly accelerating, that means it's going to be spinning faster or slower. Furthermore, in 1D kinematic motion stuff, we had the mass of our object, right? But for rotational stuff, that's going to be represented by this thing here. This variable I is called the moment of inertia. So moment of inertia. And this just details how hard it is to spin an object around the axis of rotation. So the larger the moment of inertia, the harder it is to angularly accelerate that around its axis of rotation. Much like the heavier our object, the harder it is to accelerate it, right? And so all this kind of brings us down to our final point on the table, which is that in 1D motion, we had forces, which are the masses times the net accelerations of the objects, right? And the analog of linear force is going to be torque. Torque, represented by tau, right? And so that's going to be equal to the moment of inertia times the angular acceleration. Right, so this is tau. Right. So pretty much everything we've seen in chapter 2 stuff has a rotational analog that we're going to be seeing in this chapter. So if you're really, really comfortable with things, from chapter or for like the second lecture of this course, you should be very comfortable with everything that follows. Right. So let's begin by defining angular displacement. Quick definition. Angular displacement. Just like that. So the angular displacement, delta theta, is going to be equal to our final angle minus our initial angle. Right? But normally we take this initial angle here to be 0, right? We assume that we're starting from 0. So usually the angular displacement is just, how much we've turned, through a given process. And so the angular displacement is going to have units of radians, right? Or degrees. Or even revolutions. So let me actually just move all this stuff over. So we got a little bit of space. Revolutions. Right, we can work in any of them, preferably if we're, doing work with the equations of rotational kinematics, we want to be dealing exclusively with radians, much like how when we were dealing with equations in 1D kinematics, we wanted to be working with kilograms, meters, and seconds. So the radians here is the sort of equivalent of our meter. And so let's talk about the conversion between these. So the conversion factors, right? We have 2 pi radians, 2 times pi radians is equal to 360 degrees. And that's equal to 1 revolution. Right? So we've actually got a couple of conversions here. We have, radians to degrees, right? If you just look at this part, you have degrees to revolutions if you just look at this part. And then you have radians to revolutions if you just look at these 2 things. So every single one of these is the angular displacement of an object moving around its axis of rotation a single time. Right? So next up is the concept of angular velocity. So let's define, not like that. So define angular velocity, right? We already talked about angular displacement. This is the next best step. Right, so with angular velocity, so here we're going to talk about the average angular velocity. So much like how we started our conversation in lecture 2 with our average velocity, here we're going to be working with our average angular velocity. So the average angular velocity, right, is going to be equal to omega, right, which we saw earlier was our angular displacement divided by the elapsed time. So basically, how much this thing rotated divided by how long it took to rotate that object around its axis of rotation, right? So this is equal to our final angle minus our initial angle, all divided by our final time minus our initial time. And actually, let me just box these things off. Right there, important concepts. All right. There's that. There's this, and there's our average angular velocity. Good. So this is going to have units of radians per second. Right. So it's also important to note, much like we saw in lecture 2, we're usually going to start our watches at time t is equal to 0. So usually for this delta t here, we're just going to include the final time on our watch because our initial time is just going to be 0 seconds. So really quick, let's look at a quick example that deals with angular velocity. So we have example 1. Right, example 1. So example 1 says that our sun rotates in a circular orbit. Our sun rotates in a circular orbit about the center of the Milky Way galaxy. About the center of the Milky Way galaxy. So the example goes on to say that the radius of the orbit, is a pretty big number, right? It's 2.2 times 10 to the 20 meters. It's very big. And the angular speed of the sun and the angular speed of the sun is 1.1 times 10 to the negative 15 radians per second. All right, so it takes a really, really long time for this thing to actually go around the Milky Way galaxy one time. And in fact, the problem's asking us, how long does it take for the sun to make one revolution around the center of the Milky Way galaxy? So how long does it take the sun to make one revolution? To make one revolution around the center. All right, well, let's write down what we know. So the problem tells us that our angular velocity for the sun around the Milky Way galaxy center is 1.1 times 10 to the negative 15 radians per second. Furthermore, we also know that if we want to go around the Milky Way galaxy once, right, in this circular orbit, then our angular displacement is just going to be one revolution. But we know that one revolution is equal to 2 times pi radians, right? So now looking at the definition for our angular velocity, right, we have our angular velocity, our average angular velocity, right? It's equal to our angular displacement divided by the elapsed time. And you notice that if I multiply both sides by delta t and divide both sides by our angular velocity, we get that the elapsed time, the time it takes to go around the Milky Way galaxy once, is 2 pi radians divided by omega, which is 1.1 times 10 to the negative 15 radians per second. And this gives us a time delta t of 5.7 times 10 to the 15 seconds. And that's our answer. I have no idea how long that is in years, but I'm willing to bet it's a very, very, very long time. Right? Okay, so following angular velocity, we have the average angular acceleration. So, next definition. Angular acceleration. So again, a lot of these things should look somewhat familiar, right? They should have roughly the same form that we saw, in lecture 2. So this just says that our angular acceleration, or averaging angular acceleration, is equal to our change in our angular velocity divided by time, right? And this is going to have units of radians per second squared, right? Right, so this is sort of similar to how regular acceleration is equal to the change in our velocity divided by our elapsed time, except now we're just dealing with angular stuff. So let's look at another example, this time now with angular acceleration, and we're going to call this example 2. So example 2. So example 2 says that an automatic dryer spins wet clothes Is there any after clothes? I think so. Right, wet clothes at an angular speed which is just the magnitude of the angular velocity. So this is angular speed of 5.2 radians per second. Radians per second. So starting from rest, the dryer reaches its operating speed. The dryer reaches its operating speed right, with an average angular acceleration of 4 radians per second squared. With an average angular acceleration of 4 meters or radians per second squared. 4 radians per second squared. So how long does it take the dryer to come up to speed? How long does it take the dryer to come up to speed? All right, so let's write down what we know. Right, the problem tells us that the average angular acceleration is 4 radians per second squared. Right? We know that this thing starts from rest, right? Starting from rest. So the initial angular velocity is 0 radians per second, right? Because it's not spinning. And then the final angular velocity of this thing is 5.2 radians per second. And it's asking for the time it takes in order for the dryer to actually reach that final speed. So we're going to solve this in basically the same way that we solved the last problem. So we're going to use our definition for our average angular acceleration, right, which is just the change in our angular velocity divided by the elapsed time, right? So on the left-hand side, we have 4 radians per second squared. And on the right, we have the change in our angular velocity, right? So we have our final angular velocity, 5.2 radians per second, minus our initial angular velocity of 0 radians per second. Keep running to write meters per second. Gotta make sure I don't do that. And all that is divided by delta t. And so if we multiply both sides by delta t and divide both sides by 4 radians per second squared, we get that delta t, right? It's just the change in our angular velocity divided by our average angular acceleration. Right, so punching all that in gives us a time, delta t, of 1.3 seconds. So it takes 1.3 seconds for this automatic dryer to sort of get up to its final operating speed. And so just like how 1D kinematic motion had constant acceleration equations, if you guessed, we also have constant angular acceleration equations for rotational kinematic motion. So the next section we're going to talk about are the equations of rotational kinematics. So the equations of rotational kinematics. Right. So all these are, created under the assumption that our angular acceleration for our problem is constant. So the first equation that we have says that our final angular velocity is equal to our initial angular velocity plus our acceleration, right, our angular acceleration times time, right? So a lot of these should look kind of familiar. Right, the second equation says that our angular displacement is going to be equal to 1/2 times our initial angular velocity plus our final angular velocity times time. So equation 3, our third constant angular acceleration rotational kinematic equation, says that our angular displacement can also be calculated as our initial angular velocity times time plus 1/2 times our angular acceleration times time squared. And last but not least, our fourth and final rotational kinematic equation for constant angular acceleration says that, right, our final angular velocity squared minus our initial angular velocity squared is going to be equal to 2 times our angular acceleration times our angular displacement. Okay. So keep in mind, right, that if we're dealing with a situation where our angular acceleration is 0 radians per second squared, then if we look at all this stuff and we put in 0 whenever we see an angular acceleration, right, what this essentially tells us is that our angular displacement is just equal to our angular velocity times time and that our angular velocity is just constant. Right, because looking at this first equation, if alpha is 0, then this whole term is gone, and this just says that our final angular velocity is just equal to our initial angular velocity. That is, it doesn't change. So let's look at an example. So this is going to be example 3. So example 3. And example 3 talks about a wind turbine. So a wind turbine, just a big fan really, is initially spinning at a constant angular speed. Right, whatever that is. So as the wind's strength gradually increases, the turbine experiences a constant angular acceleration. The turbine experiences a constant angular acceleration, right, of 0.14 radians per second squared. 0.14 radians per second squared. So after 2,870 revolutions, its angular speed is 137 radians per second. Right, radians per second, which is actually really fast. So the problem goes on to say, A, what is the initial angular velocity of the turbine? Right, what is the initial angular velocity of our turbine? Part B says how much time elapses while the turbine is speeding up. So B, how much time elapses while the turbine is speeding up. Okay. So writing down what we know. We're looking at part A first, right? So we know that our angular acceleration is 0.14 radians per second squared. Right? We know that the final angular velocity of our wind turbine is 137 radians per second. And we also know that our angular displacement during this whole process is 2,870 revolutions. Right? But we need to convert this into radians if we want to use it with our equations. So we know that there are 2 pi radians in 1 revolution. Right? So in this case, units of revolutions get canceled out, and we're just left with an answer in units of radians. So this is going to give us 18,032.7 radians of angular displacement. So now we want to find our initial angular velocity for our wind turbine. And so if we use equation 4, right, equation 4 says that our final angular velocity squared minus our initial angular velocity squared is equal to 2 times our angular acceleration times our angular displacement, right? So we know everything on the right-hand side. So what I can do is I can add this term, right, the initial angular velocity squared to both sides. I can subtract out that from both sides. And this is going to give me, on the left-hand side, we have our initial angular velocity squared is going to be equal to our final angular velocity squared minus 2 times our angular acceleration times, our angular displacement. And then if we take the square root of both sides, right, we get that the magnitude for our angular, the magnitude for our angular velocity is just equal to the square root of our final angular velocity squared. So 137 radians per second, squaring that, minus 2 times our angular acceleration of 0.14 radians per second squared times our angular displacement of 18,032.7 radians, right? And all this is going to be under the square root. So we punch this into our calculator. We get that this wind turbine had an initial angular velocity of 117 radians per second, right before the wind picked up. So that's part A. Now part B is asking how much time elapsed while this wind turbine was actually speeding up. So for part B, well, we know that the final angular speed, or the final angular velocity of our wind turbine, is equal to the initial angular velocity of our turbine plus the angular acceleration times our elapsed time. So what I can do is I could subtract off our newly found initial angular velocity and divide both sides by our angular acceleration to get the elapsed time. I think it's just our final angular velocity minus our initial angular velocity divided by our angular acceleration. Right, so our final angular speed was 137 radians per second. Our initial angular velocity we just found to be 117 radians per second. And our angular acceleration is 0.14 radians per second squared. And so punching that in gives us an elapsed time of 142.9 seconds. 0.9 seconds, so a little over 2 minutes. And so that we've completed the problem. So next I'd like to talk about the connections between the angular variables we've been covering and the tangential variables that they're related to. So let me start by drawing a picture so we can all get a better sense of what I'm talking about here. So our next topic is angular variables and tangential variables. Angular variables and tangential variables. All right, so the picture I need to draw is a little bit complicated, so just give me a second. Make sure that I'm not goofing this up. Right, this picture is basically gonna look like a piece of pizza. Right. Just pretend that the side length of this piece of the pizza is R, and the side length of this piece of the pizza is also R. And again, I apologize for my drawing skills. So the angle here, right, is our angle theta in radians. Here's the center or the axis of our rotation, if you want to call it. So our object starts from here, right, and it's traveling along its merry way with some velocity, vt. So this is the velocity that we learned about in the uniform circular motion chapter, except back then I just didn't call it the tangential velocity. But I did mention that it was tangential to the path at every single point. But now we're being a little bit more explicit about it. And so, it travels around this path. Maybe I can bring this down a little bit. Yeah, where I was going to take the G with me. Tangential. And so this is still velocity, but again, it's tangential to this quote unquote circular path. Right. And last but not least, we have this distance from here to here. This distance right here is called the arc length. We're going to call this S. So it's just the length of the piece of pizza crust that we travel as we go around in uniform circular motion. So that's just our arc length there. And so some relationships. So the arc length, S, is going to be equal to R times the angle that we actually travel, theta, which makes sense, right? Because S is, right, the distance you have to walk if you're walking around a circular field, right? If you go some angle theta around, then the distance you walk depends on whether you're really, really close to our angular or our, axis of rotation, but you're gonna have to walk a lot farther if you're farther away from your axis of rotation, right? So that's why our arc length here depends on how far you are, and the angle that you're going around. Number 2, the tangential velocity, right? The magnitude of the tangential velocity, right? The magnitude of these things, right? As we're going around in a circle, that's equal to the radius of our circle multiplied by our angular velocity. So it makes sense that for a given angular velocity, right, if you're close to the center of rotation, then you don't have to move as fast, right? But if you're way out here, then it's going to take a very long time to cover the same distance. So you need to have a faster velocity to compensate. So strictly put, the tangential velocity is just equal to the radius away from the axis of rotation that you are, multiplied by your angular velocity. And maybe you can guess this next one, but our tangential acceleration is equal to how far you are away times your angular acceleration. And so here, I want you guys to notice something. So we have linear stuff on the left-hand side, right? Things moving in straight lines. And on the right, we have the corresponding angular things, right? And they're connected by how far away from the axis of rotation that you are. So on the left, you have linear stuff. On the right, you have some radius times your angular stuff. So I want to touch a little bit more on this tangential acceleration because I don't want you guys getting it confused with centripetal acceleration. So the next section is going to be centripetal acceleration. Centripetal acceleration versus tangential acceleration. Right. So again, please do not confuse tangential and centripetal acceleration. Let me try and write down a picture, sort of shows what each thing is. So this is our, object moving around in a circle. And let's say that this is the center of our circle. Then we know that if something is undergoing uniform circular motion, it has, right, it must have some centripetal acceleration that points from where we are on the circle directly towards the center of the circle, right? So this is our centripetal acceleration, like we saw before. But our tangential acceleration is literally that. It's our acceleration that is tangential to the point we're on this circle with. So tangential acceleration looks like that. So if you have tangential acceleration, you're going to be speeding up, in that direction, which ends up just meaning that you're going to be going faster around the circle. So with that being said, the final section for our lecture today, I know it's a little bit of a short one, but we've seen a lot of this stuff before, kind of, with 1D kinematic motion stuff. So for our final section, we're going to be talking about things rolling along without sliding. So rolling motion without sliding. I should change colors. Rolling motion. Motion without sliding. So we don't want things to be sliding around when we're doing stuff like this, right? If you're driving and your car tires start sliding, chances are you're not in a very good situation. You're either braking really fast or you're driving, on ice. And so in this case, we're going to consider rolling motion without sliding. So let's pretend that we have some wheel, right? It's rolling along the ground, just like that. So this is the center of our wheel. Right? Now at the very edge here, this wheel is going to have some tangential acceleration. It's going to be going tangentially that way, like that. And so I want you guys to realize that the linear velocity of this wheel, like the amount that it's like the speed with which the wheel is traveling forwards, like that, that velocity is actually equal to the tangential velocity of the wheel, like at the edge. So that's just the radius of the wheel, times the angular velocity. So it kind of makes sense that the faster this wheel spins, right, the faster it moves to the right. Right, so this thing here is our linear velocity that we're all accustomed to. So linear velocity. And if you've guessed, our linear acceleration, right, the acceleration that we're all used to, is just the tangential acceleration, which is r times alpha. So the more that our wheel is angularly accelerating, right, the faster it's spinning, the better, because that means that we're speeding up. Right, this thing's rolling without slipping. So this thing here is our linear acceleration. All right, this is just the acceleration that we're used to. So let's look at an example. So last example of the day is about a motorcycle. So this is example 4. So a motorcycle, which has an initial linear speed, which has an initial linear speed. So the speed in a straight line, right, of 6.6 meters per second. So it decelerates to a speed of 2.1 meters per second in 5 seconds. So decelerates to a speed of 2.1 meters per second in 5 seconds. So each wheel has a radius of 0.65 meters. Each wheel has a radius of 0.65 meters, or 65 centimeters, but we're going to keep it in meters, and is rotating in a counterclockwise direction. And is rotating in a counterclockwise direction. And I'll explain that in a second, why they even decided to include that. So what are the constant angular acceleration, the constant angular acceleration, and B, the angular displacement of each wheel. Angular displacement each wheel. Okay. So the reason why we have these wheels rotating counterclockwise, if you guys remember, we had, when we were talking about angles and stuff, right? This was our y-axis, and this was our x-axis, right? I would always define angles relative to the positive x-axis, and I would say that if they were going counterclockwise like this, then our angles were positive, and if they were going clockwise like this, we would say that the angle is negative. So this little bit that they added here, which says that the wheels are rotating counterclockwise, that just means that our angular acceleration is positive. So our angular acceleration is positive, which also means that our angular speed is positive. And because our angular displacement, you guessed it, is also going to be positive. That just means that as we go around, our angle gets positively bigger and bigger and bigger. Right? And so that's all that means. So let me get rid of this terrible little coordinate system, and we can begin to solve this problem. Okay, so let's begin with part A. Right, so part A is asking us to find the constant angular acceleration. So part A is asking us to find the angular acceleration. But we got a bit of a problem because the problem only tells us stuff about this motorcycle linearly, right? It gives us linear velocities, right? But the good news is we know how to convert between linear stuff and angular stuff. So what we're going to do, right, we're going to use the fact that the tangential acceleration is equal to the radius of the tires times the angular acceleration of the tires. And we're going to solve this for alpha, right? So I'm just going to divide both sides by r, basically. So we have our angular acceleration is equal to our tangential acceleration divided by the radius of the tires, r. So first up, we need to find our tangential acceleration. But we know how to do that, right? Because our acceleration, tangential acceleration, just get rid of this, right? That's just the change in velocity of our motorcycle divided by the elapsed time. So we have the final velocity of the motorcycle, which is 2.1 meters per second, minus our initial linear velocity, which is 6.6 meters per second. And all that is divided by the elapsed time, which is 5 seconds. So this is going to be minus 0.9 meters per second squared. Meters per second squared. Okay. So now let's take this and plug this into here to find our angular acceleration. So our angular acceleration, alpha, is equal to this tangential acceleration that we just found, right? The acceleration going forwards. So it's going to be minus 0.9 meters per second squared divided by the radius of our tires. So that's 0.65 meters. And this gives us an angular acceleration of minus 1.38 radians per second squared. So in this case, the minus sign indicates that our wheels are slowing down, right? They're not spinning as fast, which makes sense because the motorcycle itself is slowing down. So we should expect this. So part B wants us to find the angular displacement for each wheel of the bike, right? So what does that equal? So we know that the arc length of an object traveling in a circle is equal to r, the radius of that circle, times its angle. So what does this mean? And why is this useful to us? I want you guys to think about the fact that we were to take a tire, for example, and we were to put paint all around the outside of the tire, and we were to roll it, right? So let's just take this point on a tire. Let's say that we push it forward, and it rolls until this point right here touches the ground again. So let's say that this point touches the ground again over here, right? Now at this point, the tire will have made one full revolution as it goes around. But the distance here is equal to, since this thing isn't slipping, it's just equal to the arc length S here. So this is just the arc length S. It's just the radius of the tire. But the tire has gone around one full time, so it's gone around 2 pi radians. So the reason why I bring this up is because we have a relationship between this tire rotating and how far it goes in the x direction. So in this case, we have that S, the arc length of this rotating tire, is going to be equal to the displacement of our bike, right, or this tire going forward. It's going to be this whole thing right here. But we also know that this is just equal to r times theta, or delta theta if you want, right? So the reason why I bring this up is because we know that if S is equal to r theta, then if we're trying to find our total angular displacement, right, we can divide both sides by, or this is going to be equal to delta x. And so if I divide both sides by r, then this gives us that our displacement in the x direction divided by r gives us our angular displacement. So maybe it's more appropriate to put some delta signs here, right? But since, delta theta is just theta final minus theta initial, but we're saying that theta initial is 0 radians. Right, 0 radians. Right, then I just kind of leave this off. And so as a shorthand, I just typically leave us off this delta sign here, at least in these calculations. So the thing that we're looking for, right, is given by how far this motorcycle actually travels, delta x, it's displacement, divided by the radius of each tire. So let's figure out how far this bike actually travels. So delta x is 1/2 times the initial velocity of the bike plus the final velocity of the bike times the elapsed time. That's going to be 1/2 times the initial velocity, 6.6 meters per second, plus the final velocity of 2.1 meters per second. And the bike travels this way for 5 seconds. So in this case, the total distance that the bike has traveled during this whole period of time is 21.75 meters. Okay. So now looking back, we know that our angular displacement for each wheel is going to be equal to our angular displacement divided by the radius of the tire. So it's going to be 21.75 meters, right, divided by the radius of the tire, which is 0.65 meters. And this gives us an angular displacement of 33.46 radians. So each wheel, upon moving this distance, undergoes an angular displacement, 33.46 radians. And with that, that's all I've got for you guys today. And if you guys have any questions, please feel free to ask, and I will see you guys tomorrow.